we want to talk about a way to describe graphs that you might not have heard before. Maybe you've heard it in physics when you talk about convex and concave lenses. This is concave up. Kind of looks like a bowl or a U. Concave down looks like an umbrella. Here I have a picture of a graph that changes from being concave down to being concave up. And that change happens right at the black dot. A point like that, where concavity changes, where a graph either changes from being concave down to concave up, or from being concave up to being concave down, the point where that happens is called an inflection point or a point of inflection. So I'm going to be really clear that I just fixed these over here. I see my slide didn't show up very well. All of those should be f double prime, the second derivative. So in terms of calculus, we've been using calculus to find where these interesting things on a graph happen. So a curve is concave up any place that its second derivative is positive. A curve is concave down any place that its second derivative is negative. And there is a possible point of inflection at a place where the second derivative is equal to 0, or also any place where the second derivative is undefined. So make sure you got all that into your notes. A curve, any kind of curve, doesn't have to be a function, is concave up on any interval where f double prime is positive, where the second derivative is positive. A curve is concave down anywhere that its second derivative is negative. And a curve has a point of inflection anytime the second derivative changes sign. So when you need to use calculus to look for a point of inflection, you're going to start by checking places where the second derivative equals 0 or is undefined. But it's not really a point of inflection unless the second derivative actually changes sign at that value. Just like when we talked about relative extrema, a curve has a function, f, has a critical point anytime f prime is 0 or undefined. But just because it has a critical point doesn't mean it has a relative extreme value. That the first derivative has to actually change sign before there's a relative extremum. So similarly, if we're looking for points of inflection, the second derivative has to actually change sign for there to be a point of inflection. So I see this says that there's a place for this info on your 19 facts paper. I'm now calling that your important facts paper. So there's place for all of this on your important facts paper. All right, I want to find all points of inflection of this function. So that means I'm going to need to find the second derivative of y, and I'm going to find out where that second derivative changes sign. So I'm going to start by taking the first derivative. Y prime is going to equal e to the negative x squared times negative 2x. I'm going to need the derivative of that derivative. I notice this is a product, so I'm going to use the product rule. So I'm going to say that y double prime is equal to e to the negative x squared times negative 2 plus negative 2x times e to the negative x squared times negative 2x. So this is not polynomial. This is definitely not linear. Our only real tool for solving equations that aren't linear is to use the zero product property. So that's what I'm going to do. I'm going to try to collect together all the stuff that is all the factors that these terms have in common, and try to figure out where this second derivative is equal to 0, because those are the possibilities for my points of inflection. So I see this is e to the negative x squared times a negative 2 plus, imagine I took that e to the negative x squared out to the front, and what do I have here? I'm going to have negative 2x times negative 2x, which is positive 4x squared. So here I go. I have a 0 on one side, and I have a multiplication problem on the other side. So I'm just thinking, I think of that as a dot. This is a multiplication problem, so if these two things multiply together to make 0, either e to the negative x squared equals 0, but it never can because that's me raising a positive number to some exponent. The result can never be 0 or negative. And then I'm going to take this second factor and set it equal to 0. So negative 2 plus 4x squared equals 0. I'm going to add 2 to both sides and divide by 4. I'm going to get x squared equals 1/2. So I know that x is equal to positive or negative 1 over the square root of 2. So those are two possible locations for critical points. What I need to do is make a sign chart, a number line chart, and make sure that y double prime actually changes sign at those two values. So I've made a number line chart with my two possible zero values, my two zero values marked on it. My question is, what's the sign of my second derivative on each of those three intervals? So notice I've made this sign chart and I've labeled it y double prime because right now I care about the sign of y double prime. So I'm going to try an x value that is less than negative 1 over 2. Let's say you can make it big. I'm going to make it negative 1. I'm going to say at x equals negative 1. I'm going to have e to the negative 1, e to the opposite of negative 1 squared, which is e to the negative 1, which is 1 over e. All I care about is that's positive. And inside the parentheses, I'm going to have 4 times the negative 1 squared. Negative 1 squared is 1 times 4 is 4 minus 2. That's positive. I'm going to be multiplying two positive numbers together. I'm going to have positive results. If I pick a number that is between negative 1 over root 2 and positive 1 over root 2, here's a good example, x equals 0. I care about the sign, so I'm going to have e to the 0, which is positive. And I'm going to have 4 times 0 is 0, take away 2 is negative. If I pick a number bigger than 1 over square root of 2, I'm going to end up with a positive. Times 4 times 1 squared is 4 times 1 is 4, take away 2 is positive 2, so I'm going to put positive. So this tells me that the second derivative does in fact change sign. It changes from positive to negative at negative 1 over square root of 2. The second derivative changes sign from negative to positive at 1 over square root of 2. So I'm going to write up my final answer. So here's my final answer. F of x has points of inflection. I should have said y. This is always called y. Y has points of inflection at positive and negative 1 over square root of 2 because this should say y double prime. Changes sign at those values. All right, I'll bet you $50 there's a problem almost exactly like this on the AP test. You'll have some function, a graph given to you. Notice that this graph I've been given is the graph of f prime of x, and you're going to get asked a whole bunch of questions about f. You won't be able to answer every question in the world about f, but they're going to ask you questions about where f is increasing or decreasing, where f has relative minimums or maximums, where f is concave up, that was unfortunate, where f is concave up, where f is concave down, where f has points of inflection. And given all this stuff that we just learned in 4.3, we're going to be able to answer these questions. So I'm going to answer these 5 questions. Pay close attention to the write-up, because this is what you're going to be expected to be able to do on the AP test. All right, so for question 1, for what values of x does f have a relative maximum? Why? You'll always have to, on the free response, you'll have to justify these answers. So we said, according to the first derivative test, a function f has a relative maximum anywhere f prime changes from positive to negative. So here's a graph of f prime. I want to look for a place where it changes from positive to negative. That means it changes from being above the x-axis to being below. So I see a place right here. F prime changed from positive to negative. Here, F prime was 0, so F has a critical point. But f prime does not change from positive to negative. That's not the location of a relative maximum. Here, f prime changes, but it's changing from negative, from being below the x-axis, to positive, being above the x-axis. So that's going to be my answer to number 2, the place where f has a relative minimum, because f prime changes from negative to positive. So I'm going to write up my answers to 1 and 2. All right, there's my answers to 1 and 2. F of x has a relative maximum at x equals negative 2, because f prime changes from positive to negative there. And number 2, f of x has a relative minimum at x equals 4, because f prime changes from negative to positive there. So here's a good one. Check out number 3. On what interval or intervals is the graph of f concave up? This one takes a little bit of extra work. We have to think about this one because I've been asked a question about f's concavity. To answer questions about f's concavity, I have to think about the second derivative of f, and I haven't been given the second derivative of f. I've been given the first derivative. But the good news is that the second derivative is the derivative of f prime. So I'm going to think about how f prime is changing and use that to answer my question. In general, a function f is concave up where its second derivative is positive. So what has to be true about f prime at places where f double prime is positive? Well, since derivatives are about slope, anywhere f prime is increasing, f double prime will be positive. So anywhere f prime is increasing, I'm looking for places where f prime goes uphill. Any place that f prime is increasing, any place f prime has positive slope, f double prime will be positive. So those are the two sections. That's how I'm going to write up my next part. So check this out in the write-up. I have to be very careful when I give my answer, not just to spout this stuff that I've memorized, because that f is concave up whenever f double prime is positive. Because I haven't been given f double prime. I have to give my answer in terms of the information I have. So this is how I wrote up my answer. F is concave up when x is between -1 and 1, and when x is between 3 and 5, because f prime is increasing on those intervals. So you're going to be used to giving the answer because f double prime is positive. We don't have a graph of f double prime. You have to refer back to the behavior of f prime on those intervals that tells you that f double prime would be positive. So from -1 to 1 and 3 to 5, because f prime is increasing on those intervals. So this next one, on what intervals is f increasing? Well, a function f is increasing anywhere its derivative is positive. So I'm going to look for where f prime is positive. That means f prime is above, the x-axis. Well, that's here and here. So there's my answer for number 4. So here's my statement. F of x is increasing when x is between -3 and -2, and x is between 4 and 5, because f prime of x is positive. F prime of x is greater than 0 on those intervals. This last question, number 5, at what values of x does f have a point of inflection, and why? Well, f is going to have a point of inflection anytime f double prime changes sign. I have a similar problem that I had in number 3, as I've been asked about concavity, essentially, and I haven't been given the second derivative. I've only been given the first derivative to work with. So think about this. F double prime is going to change sign anytime f prime changes from increasing to decreasing. So imagine a function that was a function that is increasing and then changes to decreasing. Well, its derivative is going to change sign because this was increasing positive slope and then has negative slope. So it's this turning around point in a function that tells you its derivative is going to change sign. So that's what we're looking for in f prime. We're going to be looking for any place f prime changes. It's not enough to say changes direction. We have to say changes from increasing to decreasing or decreasing to increasing. So I notice here, from decreasing to increasing, the derivative of this graph, f double prime, is going to change from negative to positive. So here, here, here. So I'll write this up. There you go. F of x has points of inflection at x equals -1, x equals +1, and x equals 4, because f prime changes from increasing to decreasing at x equals 1, and from decreasing to increasing at x equals -1 and x equals 4.